Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Well, that doesn't sound good, does it? Something's not right there. I wanted to play a little David Bowie, and I think my guitar is out of tune. Well, one trick that people who play guitar use to get a guitar back in tune, they first listen for the triads. That's a little better. And then they fine-tune it using harmonics. Ooh. It's a little better. I think it's there now. So basically you listen for that oscillation, it's called a beat, and you tune it until that beat stands still, essentially. You can hear it change. Now it's faster. It's pretty slow. There, that sounds better. Okay, today's lecture, lecture 92, is on beats. So the phenomenon of beats occur when you add two waves that are very close in very close to the same frequency. Okay, so if I take I could write the pressure wave as P naught times the cosine of some omega. We'll call it omega. No, we don't want omega. Sorry, kx minus omega t. Recall that the velocity is equal to omega over k. Yes. So this is a pressure wave. Pressure waves are what we hear when we hear sound, okay? So I want to consider a couple of waves that are very near the same frequency, but I want to hear it at just one place in space, okay? That's where my ear is. Remember, my ear is the measurement tool that we measure sound with, right? That's how we hear things. So we'll set x equals 0 to be at the location of my ear, so I can rewrite this in general as some p naught times the cosine of minus omega t, but cosine is actually an even function. What does that mean? That means that if I do a graph, if I draw a graph of the cosine, there, where this is some position at minus x, and this is some position at positive x, right? The values at positive x are exactly the same as the values at negative x, right? So if you pick any particular point along here, say this point here, and you evaluate it at minus that point, it'll be here. It'll have the same positive y value, okay? That's why we call it an even function. Odd functions like the sine, right, are exactly the opposite. So if I were to draw a sine on here, so if I pick some value for x over here, at minus x, it's the negative of that value, you see? Yeah. So for that reason, we say that sine functions are odd functions, okay? Okay. So that means I can write this as just p naught times the cosine of omega t, okay? Because cosine of minus omega t is equal to cosine of omega t because they are even functions. Cosine is an even function, okay? Yeah. So if I say we've got P1 is equal to, we'll give it the same amplitude just to make life easy, cosine of omega 1 times t, and we'll let P2 be equal to A times the cosine of omega 2 times t. Those are the two different frequencies, right? Yeah. Two different angular frequencies in this case. Remember, the superposition principle tells us that if this is a solution and this is a solution, then the sum of these two is a solution as well, and they just add, right? So this, I'll call it P, equals A cosine omega 1t plus A cosine omega 2 times t is also a solution, okay? But I want to rewrite this a little bit, and I'm going to use a trigonometric identity. And the identity I want to use is the cosine of A plus the cosine of B is equal to 2 times the cosine of A minus B over 2 times the cosine, I ran out of room here, huh? A plus B over 2. Okay? This is just a trigonometric identity that you can find in any trig book or on any trig website. And so we're going to use that here, where our A is going to be omega 1 times t, and our B is omega 2 times t. So we can rewrite this as P equal P naught. I meant to, A is supposed to be P naught, I'm sorry. P naught That's the maximum pressure. Well, P naught times the cosine of omega 2 minus omega 1 divided by 2 times T times the cosine of omega 1 plus omega 2 divided by 2 times T. Yes? That's just using this trigonometric identity, okay? And when I do that, I can think of this like this. I can say, well, here I've got some P times, I'll call it P with a tilde times the cosine of omega 1 plus, and I'm actually going to call this omega with a bar over it, okay, times T. Where P tilde is equal to P naught times the cosine of, I'm going to call this delta omega times T. And delta omega is just the frequency difference, omega 2 minus omega 1, right? It's the difference in the frequencies, okay? And the omega bar is just the average of the frequencies, okay? So if the frequencies are very close, right, then the average is about the same as either of the frequencies, right? If they're almost the same frequency. So we could, if we wanted to, just simply say that in some extent, that P is equal to this P tilde times the cosine of omega T. Okay? And I'll write it as approximately, like that. So what this is telling us is that if I were to graph the amplitude, this P tilde, and look at it, what does it look like? Graph P tilde as a function of time, looks like this. It looks like another cosine, right? Whose angular frequency is proportional to the difference in the two frequencies of the waves I'm adding. So when I was on the guitar, I was mixing two tones, one of frequency omega 1, one of frequency omega 2, and I'm trying to make them the same. And so I'm listening for this beating, right? It's this getting loud, getting soft, right? So here it's loud, right? Here it's soft. That's what's causing that beating effect, that wah, 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 right?
Yeah.
It's that modulation in the amplitude caused by this difference in frequencies, okay? And when that modulation stops, right, that means that delta omega is equal to 0 and those two frequencies are the same, and my guitar string is in tune, you see?
Yeah.
So if we were to look at, let's make a little room here for it. So here we can look at this effect, right? And we see that the sum of those two waves, when you add them together, in some places they come in phase, right? They get very close to being in phase. And in some places they're not in phase, they're misaligned. So when they add together, their amplitude decreases, you see? And this gives you these little wave packet looking things, which is the beating phenomenon. So you can see several beats in this figure here, right?
Yeah.
And that's the beating that you're hearing. So this is just P versus time, right? That's what we're seeing here. Make sense?
Yeah.
Now the fast oscillation, you see, well, that's just really the original omega, right? That's the note I was trying to tune to. So that's that angular frequency, and then the modulation of that wave packet, that's coming from this delta omega, okay? The fact that they may be a little bit different, okay?
All right.
And so that's the phenomenon of beating. It's pretty straightforward, and it's a consequence of the superposition principle. Any questions about it?
No.
Have you heard beating? Can you think of an example of where you've heard beating before?
You like your music?
Mhm.
Yeah.
When you pick up, I think this is beats, when you pick up a telephone, you hear that telephone noise,
Yeah.
right? I believe that is created by mixing two pure tones to create this beat. So it's just, if you listen to it, you can hear the oscillation, okay? That's the modulation of the amplitude. Louder, softer, louder, softer.
Yeah.
Okay? So next time you pick up a telephone and listen to it, you hear the carrier signal, see if you can hear the beat frequency in it, okay?
All right.
All right, that's all I have on that. That's beats.